Infinity and infinitesimal. These concepts often spark debate. They seem intuitive, but they're also hard to grasp. This time our theme is the infinitesimal, but infinity and infinitesimal are two sides of the same coin. So, first, let's think a bit about infinity. I'll explain a simple common way of thinking about infinity. Roughly speaking, infinity means something endlessly big. Here's a number line. So where is infinity on it? It kind of feels like it's way out there in the positive direction of the number line. Infinity is bigger than any number on the number line. Since it's in the positive direction, we call it positive infinity. On the other hand, if you go far in the negative direction, you get negative infinity, or so it seems. But here's some disappointing news. At least, there's no such number as infinity on the number line. Why is that? Let's suppose for a moment that there is a number called infinity on the number line. This dotted line just means we're skipping a huge distance. Imagine that far to the right of 0 there's a number called positive infinity, and it's bigger than any number. That's the situation we're imagining. But if you add 1 to it, you get an even bigger number. Positive infinity is supposed to be bigger than any number, but now there's a number even bigger than that. That's a contradiction. Therefore, infinity isn't a number that exists on the number line. But let's not go too deep into this right now. Next, let's think about the opposite of infinity, an infinitesimal. An infinitesimal is something infinitely small. More precisely, it's something infinitely close to 0, but isn't actually 0. That's the idea behind an infinitesimal. Back then, I had no idea how scary this concept really was. Oh man! Another weird problem showed up.
This is troubling indeed. We must choose whether to solve this problem or not.
Yeah, you're right. Wait, we don't have to solve it? Then let's not solve it.
Don't say that. Let's think it over once more. We must choose whether to solve this problem or not.
Wait, didn't you just say the same thing? Ah, I see. So this is what's called an infinite loop. Looks like we have no choice but to solve it.
Excellent.
By the way, this problem, there's a number line drawn here. And above it, it says, where is an infinitesimal? Is there even an infinitesimal on the number line?
Let's think about it for a moment. An infinitesimal is something infinitely close to 0. More precisely, it's closer to 0 than any other non-zero number. That's what an infinitesimal is.
I see. So it's super close to 0. Then maybe an infinitesimal is here? Let's use epsilon to represent an infinitesimal.
That's interesting. Zundamon just put epsilon a tiny bit to the right of 0. That means you're imagining a positive infinitesimal.
Yeah, exactly.
Now let's zoom in near the origin. Epsilon is close to 0, but not equal to 0. So there must be a gap between 0 and epsilon. In other words, there are other numbers between 0 and epsilon, like epsilon over 2, for example.
There's another number between them? That's a problem. Epsilon is supposed to be an infinitesimal, so it should be closer to 0 than anything else. But epsilon over 2 is even closer to 0. Something weird's going on here.
Yes, no matter how close epsilon is to 0, there's always a number even closer. Therefore epsilon can't really be called an infinitesimal.
So, does that mean infinitesimals don't exist on the number line? That's kinda disappointing.
Don't give up just yet. Let's think a bit more.
Even so, if I place epsilon here, there's always a number even smaller than that. So I try making epsilon even smaller. And still there's always a smaller number. No matter how small epsilon gets, a smaller number always exists.
That's true. But think carefully. Right now, you are actually doing something very important.
Wait, really? Something very important. But I was just making epsilon smaller and smaller. Ah, I get it. I was making epsilon smaller and smaller. That means I was making it get closer to 0. Could this be what an infinitesimal really is?
Brilliant! An infinitesimal isn't a constant. It might be a variable that gets closer and closer to 0.
An infinitesimal is a variable, not a constant. That does explain how it can take on arbitrarily small values. An infinitesimal can be closer to 0 than any non-zero number.
The same idea applies to infinity too. Infinity isn't a constant either. It's a variable that grows without bound. With that view, infinity really can be bigger than any number.
You're right. Alright, problem solved. Wait. I feel like something's off here. An infinitesimal is a variable that approaches 0. That sounds like an interesting idea at first. That would let it get closer to 0 than any non-zero number. But even if it keeps approaching 0, epsilon doesn't take on an actual infinitesimal value. If you pick out a value of epsilon at any point, it's still just a number. And there are still infinitely many numbers closer to 0 than that. Can we still call epsilon an infinitesimal?
You've realized it, haven't you? Yes, there's a problem with that interpretation. We treated the infinitesimal as a variable, but what we really want is for an infinitesimal value to exist. We want to believe in the existence of an infinitesimal constant. To put it another way, that means we want to express the dynamic process of approaching 0 as a static value.
Turning something dynamic into something static. Is there really a way to make that happen?
Okay, how about this approach? Let's look at the number line again. Now consider a sequence like epsilon sub 1, epsilon sub 2, epsilon sub 3, and so on that gets closer and closer to 0. Let's denote this sequence as epsilon.
This is showing the approach to 0 as a sequence. And we're thinking of the sequence itself as the infinitesimal.
Exactly. The sequence itself is the infinitesimal. This way we can describe the dynamic process of approaching 0 using the sequence epsilon. But the sequence itself doesn't change, because each of its terms is fixed. So epsilon can be seen as a fixed constant.
We managed to represent the dynamic process as a static sequence. That's such a cool idea.
By the way, there are many ways to approach 0, so remember, there's more than one infinitesimal. An infinitesimal that approaches 0 faster or gets close to 0 earlier can be considered smaller.
Got it.
And this same idea works for infinity too. Take a sequence like omega sub 1, omega sub 2, omega sub 3, and so on, that keeps growing without bound. If we write this sequence as omega, then omega can represent positive infinity.
I see.
Since there are many ways to grow, we can say that some infinities are bigger than others.
That's really interesting. So we can express both infinities and infinitesimals using sequences. But can we actually use this in calculations? How would we even do math with infinities and infinitesimals?
Don't worry, I've got a great idea.
What?
But first, let me explain how to treat real numbers, the ones on the number line, as sequences too. It's super simple. You just take any real number a, and match it with a constant sequence where every term is a. Well, a constant sequence just means one with the same value repeats forever.
I see what you mean. So it starts with a, and stays at a the whole time. Yeah, that definitely feels like it represents the real number a. Now we can treat real numbers as sequences too.
Yeah, we can represent real numbers, infinities, and infinitesimals using sequences. All that's left is to define arithmetic for sequences, and then we can start doing calculations with infinities and infinitesimals.
Okay, this is getting tricky.
It'll make sense once you try it. To do math with infinities and infinitesimals, we need to define arithmetic for sequences. First, let's say we have two sequences, alpha sub 1, alpha sub 2, alpha sub 3, and so on as alpha, and beta sub 1, beta sub 2, beta sub 3, and so on as beta. We define the sum of two sequences as adding each pair of terms to make a new sequence. So the new sequence alpha plus beta would be, first term is alpha sub 1 plus beta sub 1, second is alpha sub 2 plus beta sub 2, third is alpha sub 3 plus beta sub 3, and so on.
That's a simple definition.
Likewise, we define multiplication as multiplying each pair of terms to make a new sequence. So the new sequence alpha beta would be, first term is alpha sub 1 beta sub 1, second is alpha sub 2 beta sub 2, third is alpha sub 3 beta sub 3, and so on. We can define subtraction and division the same way. Just be careful not to divide by 0 in division.
I think I'm getting it.
Then let's try doing an actual calculation.
Bring it on.
The most basic example is arithmetic with real numbers. Let's say a and b are real numbers. Earlier, we explained how to represent real numbers using sequences. We'll just identify a real number with the constant sequence that corresponds to it. Let's not worry too much about making this rigorous.
That's pretty bold.
Now, what happens if we add two such sequences?
Wait. If we add the first terms, we get A plus B, so that's the first term. The second terms also add to A plus B, so the second term is the same. And that continues forever. A plus B every time. So this is basically the sequence that represents the real number A plus B.
Addition of real numbers and sequences matches up perfectly. Alright, what about multiplication?
I think we can handle multiplication the same way. The first terms multiply to AB, and so do the second terms. And it keeps going with AB forever. So this is the sequence that represents the real number AB.
Looking good. Now we see that doing arithmetic with constant sequences of real numbers is basically the same as doing arithmetic with real numbers.
So we got natural definitions for arithmetic operations on sequences. Well, what happens when infinitesimals get involved?
Good question. So next, let's look at a sequence like this. What kind of number do you think this sequence represents?
That's a tough one.
Let me give you a hint. 2 is 1 plus 1. 3 over 2 can be written as 1 plus 1/2.
What are you doing? Not sure I get it, but I'll keep going. 4 over 3 is 1 plus 1/3. And 5 over 4 is 1 plus 1/4. So that means every term has a 1 in it. Let's try separating out the 1s for now. Then we're left with the sequence 1, 1/2, 1/3, 1/4, and so on. By the way, this plus sign means sequence addition, just like we defined earlier.
Nicely broken down. The first sequence is all ones, so it represents 1. The second sequence has increasing denominators. It gets closer and closer to 0, so it represents a positive infinitesimal. If we call this sequence epsilon, then the answer is 1 plus epsilon.
That's an interesting result. This sequence represents 1 plus a positive infinitesimal, so it's a number just a tiny bit more than 1.
It's kind of exciting to see an infinitesimal show up in a calculation. Let me just quickly show you one last example. Let alpha be the sequence 2, 4, 8, 16, and so on, doubling each time. Since it grows without bound, it represents positive infinity. On the other hand, let beta be the sequence 1, 1/2, 1/4, 1/8, and so on, having each time. This one gets closer and closer to 0, so it's a positive infinitesimal. If we multiply these two sequences, we'll skip the steps, but the result is a constant sequence of 2's, so it represents 2.
Multiplying infinity and an infinitesimal gave us a finite value. That's kinda weird.
Of course, there are many kinds of infinities and infinitesimals, so their product isn't always 2, and it's not always finite either, so be careful.
Got it. By treating sequences like numbers, we can handle infinities and infinitesimals like numbers too. That's a brilliant idea.
Watch out, Zundamon! Something's coming!
What? Whoa, this is? What kind of sequence is this?
It starts with 1, then 2, and after that it's 3 over and over. I wonder what number this sequence actually represents.
Okay. Ignoring the first two, it stays at 3 forever. If this does represent some number, then it makes sense to say it's 3.
You're clever today, Zundamon.
Wait, what do you mean today?
Indeed, if we ignore the first two values, we can treat this as the sequence that represents 3. So we can consider this original sequence as representing 3. More generally, we can use the idea of ignoring a finite number of terms. In other words, sequences that are the same except for a finite number of terms are treated as equal. That allows us to interpret more sequences flexibly.
Hold on, Metan. I think something else is coming.
What?
This
is?
What is this? Alpha is the sequence 1, 0, 1, 0, 1, 0, and so on. It's alternating between 1 and 0. Beta is the sequence 0, 1, 0, 1, 0, 1, and so on. Very similar to alpha, but alpha starts with 1, while beta starts with 0.
They alternate between 0 and 1, so these sequences are oscillating. They don't diverge to infinity and they don't converge either. So what kind of numbers do alpha and beta represent?
No idea at all. What should we do?
Why don't we try calculating something with them?
Calculate what?
Let's start with alpha plus beta. What do you think that looks like?
Wait. First, 1 plus 0 equals 1. Next, 0 plus 1 is also 1. Then 1 plus 0 again, still 1. And it stays 1 from there on. So alpha plus beta is a sequence that represents 1.
That seems right. Okay, what about alpha beta?
Let's see. The product of alpha and beta is... First, 1 times 0 is 0. Next, 0 times 1 is 0. Then 1 times 0 is 0 again. And it keeps being 0. So alpha beta represents 0.
This is getting interesting. To summarize, the sequences alpha and beta satisfy these relations.
Add them to get 1. Multiply them to get 0. That's a simple relationship.
Here, even though we're just dealing with sequences, let's assume we can calculate with them just like real numbers. Then from alpha beta equals 0, we can say at least one of alpha or beta must be 0. We don't know which one is 0 though. Now look at the equation alpha plus beta equals 1. Either alpha or beta is 0, so the other must be 1.
Alpha and beta are 0 and 1. But which is 0 and which is 1? This is getting confusing. Both alpha and beta alternate between 0 and 1. But alpha starts with 1, beta starts with 0. One of these sequences corresponds to 0 and the other to 1. So which is 0 and which is 1?
Since both sequences alternate between 0 and 1, we can't clearly say which is 0 and which is 1. And this brings us to the issue of identifying sequences as the same.
What do you mean?
The sequence alpha alternates between 1 and 0. Should we consider it equivalent to the all 0 sequence? Or should we see it as equivalent to the all 1 sequence? We have to choose one or the other. But we can't clearly justify either choice. And this story doesn't end here. Actually, with a method called ultra power, we can resolve this identification issue.
Wait, you knew about that?
Unfortunately, this method is too advanced to explain here.
I feel like I just saw something forbidden.
But just to give you the general idea, this method makes sure that calculations between sequences don't cause problems by creating a rule for identifying sequences. More precisely, we can prove that such a rule exists, but we don't fully understand what that rule looks like.
So we can prove the rule exists, but not actually describe it. That's kinda mysterious. By the way, about those sequences alpha and beta, one of them is 0 and the other is 1. So which one is which in the end?
Actually, both cases are possible, because there are many different identification rules. Depending on the rule, alpha is 0 and beta is 1. Or it could be the other way around, alpha is 1 and beta is 0.
What? I thought we were getting answers, but now it's even more confusing.
I understand how you feel. Anyway, with ultra powers, we can extend the real numbers to include infinite numbers and infinitesimal numbers, constructing what's called the hyperreal numbers.
Hyperreal numbers. That sounds kinda cool. But what are they used for?
One major use of hyperreal numbers is in a field called non-standard analysis. Put simply, it's calculus done using hyperreal numbers. Normally, you can't treat infinities or infinitesimals as numbers. But in non-standard analysis, calculus is developed using an intuitive approach that directly involves infinities and infinitesimals.
Non-standard analysis. What a cool name!
By the way, there are many ways to deal with infinities and infinitesimals in math. Just remember, hyperreal numbers are one of the main approaches.
Thanks for watching.
If you'd like to support this channel, consider becoming a member. In this video, we talk about the purpose of our membership. Check it out if you're interested. Well then, take care everyone.
See you later.